No.
Good morning to all participants present over here. Hope you have gained sufficient knowledge over this last 5 days, 4 days, from 14 to 17. Today is the 5th day of the STTP, and today I request Dr. P. Usharani, Professor and Convener of AACTE STTP3, to provide an introduction about today's session. Presenter. Thank you, madam.
A very good morning to all. I welcome today's resource person, Dr. Umamaheswari, Professor, Rajalakshmi Engineering College, and all participants for the 5th day of STTP. Dr. Umamaheswari is currently working as Professor in the Department of Electrical Electronics Engineering, Rajalakshmi Engineering College, Chennai, Tamil Nadu. She has obtained her BE degree in Instrumentation Control Engineering from Government College of Technology, Coimbatore, and her ME degree in Electrical Drives and Embedded Control, and doctoral degree in the area of power quality from College of Engineering, Anna University, Chennai. With a teaching experience, research experience of more than 20 years, she has presented more than 30 papers in high-impact international journals, international conferences. She is a recognized supervisor for doctoral degree program under Faculty of Electrical Engineering at Anna University, and she is guiding several PhD, completed 3 faculty members, doing 5. She is a reviewer of many reputed international journals. She is a life member of professional bodies like IEEE, ISOI, and ISTE. Her research areas of interest include power quality enhancement using power converters, applications of linear and non-linear controllers to renewable energy systems. I once again welcome you, ma'am, and deliver the topic, design of DC to DC converter based power factor corrector using linear quadratic regulator control for single phase as well as 3-phase systems. I request you to hand over the session to you, ma'am. Kindly take the session, ma'am. Thank you.
Okay, thank you. Thank you for the nice introduction, Dr. Usharani.
Thank you.
Am I audible?
For invitation, Uma madam.
Okay, thank you. Okay, thank you for inviting me to the STTP on power quality issues. I thank Dr. Usharani ma'am for inviting me. So I will just start my session now. Shall I start, ma'am?
Yes, ma'am. Yes, ma'am.
Okay. The topic I have chosen is...
So kindly share the slides, ma'am. Madam.
Okay.
Kindly share the slides.
Okay. One second.
Yes.
Is it visible now?
Now it's 1 minute.
Is it visible?
No, presentation. Yes. Full view. Full screen.
Full view. Okay. One second.
Okay.
Now?
Fine.
Shall I proceed?
Yes, ma'am.
Okay. Thank you. Okay. The topic I have chosen is design of DC to DC SEPI converter based power factor corrector using linear quadratic regulator control for single phase and 3-phase systems. Okay. Whatever power factor corrector we are designing right now, it is meant for SMPS, switched mode power supply. As you already know, in the case of switched mode power supply, you are going to have a front-end AC to DC converter, which is going to be your rectifier, followed by a DC to DC converter. So by operating the DC to DC converter MOSFET switch with very high switching frequency, we are just emulating the DC to DC converter as a resistor such that my source voltage and source current will be in phase. So I have the power factor which is close to unity. Okay, this is my objective. Okay, let me start from the outline. So the outline of my presentation is, it is starting with overview, proceeded by introduction, next methodology, then results and discussion, conclusion. Okay, this is the outline of my presentation. Coming to the overview, to model and design DC to DC SEPIC converter based power factor corrector using cascades and control strategy. Though I have given a topic like DC to DC converter, but here I have chosen DC to DC SEPIC converter for doing the power factor correction because of the advantages which will be presented in the consecutive slides. Okay, next we are implementing cascade control strategy here using outer PI and inner LQR controller. You need to construct a simulation model of DC to DC converter based power factor corrector for single phase and three phase system. Finally, after designing a controller using the MATLAB, we will be just seeing how the performance of the converter for outer PA and inner LQR controllers. Okay, we will just compare the performance of the LQR controller with the conventional PA controller in order to show the effectiveness of the proposed LQR controller. This is just the overview of my presentation. So coming to the introduction, prior starting why we are choosing DC to DC converter, for that we need to know the importance of the DC to DC converter. So as I said already, the power factor correction we are implementing in SMPS setup. In your switched mode power supply, in the front end, you are going to have a AC to DC converter, which is nothing but a bridge rectifier, followed by a DC to DC converter. Okay, this is what is present in the case of your switched mode power supply. So this switched mode power supply is used in personal computers, battery chargers, and mobile phones and spacecraft applications. Here I have listed out only few applications. Apart from that, you have many applications for your switched mode power supply. So the input current of your switched mode power supply has high harmonic component. Why? Because you are having a switching devices like MOSFET, IGBTs in your DC to DC converter, and even diode is a nonlinear device because diodes we will be using for constructing a AC to DC converter. So diodes and power electronic switches present in the front end AC to DC converter and DC to DC converter is going to create a harmonic problem. So we want to suppress the harmonic. Before going to the suppression of the harmonic, what are the effects of harmonic you should know. So whenever you are having harmonics in the system, what happens is the power available to the utility grid gets reduced. That is the first thing. And the second important disadvantage is you have EMI problem, and sometimes this harmonic will interfere with the consecutive equipment present nearby. So that is going to make the device to operate not in a proper way. So this will create EMI problem and you have a cross interference problem. Okay, so for suppressing that harmonic, we are just using a DC to DC converter itself. So whenever we are suppressing the current harmonic, what happens is your input current will be in phase with the supply voltage, so that you can have maximum, you can extract maximum real power from your supply voltage. That is your objective. And the fourth thing is, when you add a power factor corrector in your SMPS setup, what happens is you are minimizing the losses because you are suppressing the harmonic. Because of the presence of harmonics, you have more losses. So when you suppress the losses, what happens? Your efficiency of the overall system will improve. Okay, this is one more advantage. And whenever you are having harmonic problem, what happens is, I said already, you have the device which is present nearer to the device, whatever we are operating, that will get affected. So in order to avoid that, you need to suppress the harmonic. For that purpose only, we are using DC to DC converter as a power factor corrector in the SMPS setup. Okay. That is one more advantage, and the last advantage is going to be we are just going to operate the DC to DC converters switch by means of a high frequency PWM signal. So when you operate the DC to DC converter MOSFET with very high switching frequency, what happens is you are having the I mean, you are when you want to construct a DC to DC converter, you will be using a MOSFET switch, inductor, capacitor, and all. So when you operate at high switching frequency, what happens? The component size, that is the passive components, inductor, capacitor size will get reduced. That is one important thing. And one more thing is, when you are operating at high switching frequency, actually what happens is the circuit is going to behave as a resonant circuit. Because of that, what happens? The inductive capacitance and capacitive reactance both will get equal value. So your XL will become XC. The inductive reactance and capacitive reactance both will be equal. Because of that, your circuit is going to behave as a resistor circuit. So whenever you are having a diode rectifier with a resistor, what happens? Your voltage and current will be in phase. Thereby, you are maintaining a power factor which is equal to unity. So these are all some importance of your SMPS setup, and how we are just incorporating the power factor correction circuit in the SMPS itself in order to overcome these disadvantages. Okay, next coming to power factor, as you already know, it is nothing but the ratio of real power to the apparent power. Real power usually you will be measuring in terms of watts, and apparent power it is in terms of volt amperes. So in your real power, if you want to measure, you need to measure the instantaneous value of your current and voltage. Okay, in your real power, you have one term called cos phi. Okay, that cos phi is cosine of the angular displacement. That angular displacement is nothing but a displacement angle present between the source voltage and the source current. So apparent power is nothing but the product of RMS value of the voltage and current. Okay, so when you measure a real power and when you measure a apparent power, so if you divide the real power by apparent power, you will be getting a power factor. Now suppose say your voltage and current, if both are sinusoidal and are in phase, what happens is your power factor is going to be unity. In that case, your real power and apparent power will be equal. So you will get cos phi as unity. Suppose if your real power and apparent power, if both are not equal, definitely there is a displacement angle. There is an angle difference between your source voltage and source current. Because of that, what happens? Your power factor will not be unity in that case. Okay, this is one way of finding out the power factor by using real power and apparent power. Okay, so coming to your voltage and current. Suppose if voltage and current both are in phase, as I said already, your power factor is going to be unity. But sometimes what happens is your voltage and current will be in phase, but your current waveform will be distorted because of the presence of harmonics. In that case, you need to look into one more factor called distortion factor. The distortion factor is actually representing the amount of harmonics present in your source current or source voltage. Okay, so you need to concentrate on distortion factor. So you need to have some measure for measuring the distortion factor. So we have one in these index called total harmonic distortion. Based on total harmonic distortion, you can measure your power factor. Okay, because when you are using your total harmonic, when you are calculating your total harmonic distortion, indirectly you can calculate your power factor, because there is an expression which relates your total harmonic distortion and power factor here. So what I mean to say here is, whenever the voltage and current are in phase, we will just think that since both are in phase, you will have a power factor which is equal to unity. Why? Because you will be just finding out the displacement angle, that is the phase angle difference between the voltage and current in that case. But what happens is, suppose if you have a current which is containing so many harmonics, because of that, what happens? The shape of the current would be a sinusoidal one, but it is in phase with the source voltage. In that case, if you calculate the displacement factor, that is going to show 0. So you will assume that your power factor is unity, because cos 0, if you calculate, you will be getting the value as unity. But you need to focus on one more factor called distortion factor, just to find out how much amount of harmonics present in your source current. Because finding power factor alone is not sufficient. You need to concentrate on the factor called distortion factor. The distortion factor is being measured by using the tool called total harmonic distortion. When you measure total harmonic distortion, indirectly you can calculate the value of your power factor. There is an expression which relates the total harmonic distortion and the power factor. That's it. Okay, so now how to calculate the total harmonic distortion? Total harmonic distortion is nothing but square root of the sum of the harmonics, the harmonic current, but you need to exclude the fundamental current. It is going to start from the second harmonic to the nth harmonic. Okay, square of second harmonic to the n, sum of square of n, second harmonic to the nth harmonic divided by the fundamental current. Okay, you can see that the value of P is going to be 2 here. Okay, in that way you can calculate the total harmonic distortion. From this expression, what is the inference you are making is whenever the fundamental current, if it rises, what happens? Your THD percentage will get reduced. So when THD gets reduced, what happens? Your power factor increases. So you can see the relationship between your power factor and the THD here. Okay, so whenever you have low percentage THD, what happens? You will be able to attain a power factor equivalent to unity. Okay, suppose say let us assume the THD is going to be 0%. By just looking at the expression, you can realize cos theta is equal to power factor, which is being represented as power factor. So when THD percentage is 0, what happens? The power factor becomes unity. Okay, so what is that we are going to do in the case of your SMPS is we are just going to control the switch and make the switch to operate at a resonant conditions. Okay, when it is operating at a resonant condition, what happens? Source voltage and source current will be in phase. So you have the displacement angle almost equivalent to 0. Because of that, you can attain the unity power factor. So what is power factor is the process of shaping the input current is called power factor. So in your SMPS, you have one relation which relates total harmonic distortion and power factor. Here I have given the expression, that is power factor is equal to square root of 1 by 1 plus THD square. So this relation just shows that whenever you reduce the harmonic content, what happens? Your power factor gets improved. Okay. So when you have less THD percentage, indirectly you are making the power factor close to unity. So THD is nothing but a total harmonic distortion. As I said already, it is nothing but a square root of sum of the harmonic component starting from second harmonic to nth harmonic divided by the fundamental component. So whenever the THD is 0, what happens? Power factor will be close to unity. Okay. So what are the design issues we need to consider for designing a power factor corrector is, these are all some design parameters you need to consider. You need to consider the size. So as I said already, you are going to operate the MOSFET switch with very high switching frequency. If you operate the MOSFET switch with a very high switching frequency, what happens? Your circuit will come into resonance condition. So whenever the circuit will come into resonant condition, what happens? Your XL will be equal to XC, and you are going to construct a set. You are going to emulate the circuit as a resistor actually. Okay, so when you look at the size, since you are operating at very high switching frequency, what happens is the passive component size will get reduced. As you already know, your XL is equal to 2 pi FL and XC is equal to 1 by 2 pi FC. Because of that, whenever you operate a DC to DC converter with a very high switching frequency, what happens? Your XL and XC value will get reduced. So because of that, the component size will get reduced. So when you reduce the passive component size, naturally the structure of the overall system will be very compact and the size will be very small. Okay. Next factor you need to consider is cost. When you look at the cost, compared to other power factor corrective methods, this setup will have less. It requires very low cost. It is cost effective. Why? Because we are doing the power factor correction by just using a DC to DC converter itself. In SMPS, you have so many options for doing the power factor correction in SMPS. So cost wise, it is affordable. Okay, coming to the efficiency, since we are focusing on the harmonics, so our objective is to suppress the harmonics. So as we suppress the harmonics, what happens? your power supplied by the supply voltage. I mean, whatever power you are acquired from the supply voltage, it is going to be a pure real power. It doesn't contain any reactive power. So your input power will also be good and the power quality is good. Naturally, you will get a more output power also. Your efficiency will get reduced because of the reduction in losses. Okay. So when you suppress the harmonics, what happens? The losses will get reduced. When the losses will get reduced, what happens? Your efficiency will get improved. Okay. And the fourth important parameter you need to focus on is when you are designing a power factor corrector, you need to look into the measure called percentage THE, that is total harmonic distortion. Okay, as I said already, it is nothing but the ratio of what square root of summation of the harmonic starting from second to the nth harmonic divided by the square of the fundamental harmonic. That is a formula for calculating THC. So you need to construct a PFC, power factor corrector, in such a way that your percentage THC is very low. In such a case, you can attain a power factor which is very close to unity. So this point is very, very important. And fourth one is going to be a speed of response. That the speed of response that depends on the controller you are going to design. Okay, so you need to choose a controller in such a way that your speed of response will be very good, so that you can attain the output voltage in a with a minimum settling time. Okay, under different operating conditions. Even I have shown different variations. You can vary the load, or you can vary the set point, or you can vary the line. Okay, so irrespective of the variation in your operating condition, your controller should be effective enough to produce a regulated output. Okay, so in that way you need to construct a power factor circuit. Though I am focusing on power factor here, but in my SMPS my objective is to get a regulated output voltage and I need to correct the source current. Okay, these are all two objectives. So I need to regulate the output voltage as well as I am going to do the corrective action, because after all from SMPS we are going to get only a DC power. That DC power is supplied to DC applications. If it is so, I need to provide a regulated output voltage to the DC applications. So I need to carry out the correction in such a way that my controller is sufficient enough to do both the objectives. Okay, the first objective is regulated output voltage, and the second objective is to correct the source current so that I am attaining a power factor very close to unity. Okay, and the fourth factor you need to consider is robustness and stability. Okay, you need to design a controller in such a way that your system is very robust. Suppose if I am operating under different conditions also, what happens? It has to provide a regulated output voltage as well as it has to provide a input current which will be in phase with your supply voltage, such that you are maintaining a power factor close to unity. So it should be robust under different operating conditions, and it should be stable in different operating conditions. So in order to satisfy these objectives, we'll be designing a power factor corrector by using a DC to DC converter. So what are the objectives of my power factor corrector is, it should be simple to implement and it should occupy small size. Since I am operating the switch with a very high switching frequency, naturally the component size, that is passive components, whatever I am going to use, that component size will get reduced. Because of that, what happens? Your size of the entire system will be very compact. Okay, and it should not involve more number of components, and it should offer low cost. Okay, actually whatever design parameter I have quoted, that will be aligning with the objectives. Okay, and it should offer high efficiency, because after all my objective is to mitigate the harmonics. If I mitigate the harmonics, naturally my losses will get reduced. When I reduce the losses, what happens? Output power will increase. So when you have an increase in output power, naturally your efficiency will increase. Okay. And the fourth thing is, should reduce the input current distortion and offers low percentage THC. Then the fifth and sixth point is almost related to robustness. My controller should be in such a way that it is providing a regulated voltage and the effective source current shaping in the presence of line load and set point variation. Okay, I can give these three variations and I need to check the performance of my converter, whether it is providing a regulated output voltage and the sinusoidal source current. Irrespective of these variations, I need to look into, okay, so that I can see the effectiveness of my DC to DC converter. These are all some typical waveforms which shows what are the harmonics percentage when you have different types of loads, starting from inductive to AC to DC drive. If you adjustable speed drive, if you use, what happens to the percentage THD? It will be more than 50%. And if you use an inductive load, naturally you know that in the case of inductance, your current lacks the voltage, so you have a lacking power factor with a THD of 40%. If you use capacity load, you will be having a THD percentage less than 40%, but it is going to be a leading power factor. Why? Because the current leads the voltage in the case of capacity load. Similarly, they have given a set of devices which will have the THD percentage along with the THD percentage they have listed out. Okay. Next, coming to your reason why we are getting a harmonics in the case of your SMPS setup. I said already in your SMPS setup, you are going to have a single phase supply or three phase supply. Along with that, you will be connecting a AC to DC converter as a front end converter, okay, which is going to be a bridge rectifier preferably, followed by a DC to DC converter. This is a setup you have in your SMPS. So in your AC to DC converter rectifier, if you look at, you will be getting a output voltage from your rectifier, which is going to be a unidirectional DC. You want to have a constant DC, for that you will be connecting a capacitor. So when you connect a capacitor, what happens? You will be getting a DC bus voltage, whatever is shown as U here, but because of the connection of capacitor at the output side, though it removes the ripples in the output voltage, but it is going to distort the current. So you can look into the DC bus capacitor current, which is represented as IC here. So your DC bus capacitor current will be IC. So when you have some current distortion at the output side, what happens? That is definitely going to impact your source current. So your source current will get distorted. So your source current, they have given us a third waveform. You can see that the source current is a distorted one. After that, because of the presence of harmonics in the source current, what happens? Your source current is not purely sinusoidal here. What happens? This source current, when it reacts with the source impedance of your supply, what happens? Your source voltage will get distorted. So your source voltage, you can see, you will have some dip in the source voltage. It is not a pure sinusoidal one. It is also get corrupted here. Okay. This is the reason for harmonic generation in the case of your DC to DC converter, which is constructed in your SMPS setup, which is included in your SMPS setup. Am I clear? Am I clear? Am I clear?
Yes, ma'am.
Yes.
Sir, you told that accountancy, you told.
I'm just talking, follow your question. Just tell me. Just repeat your question. Just repeat your question. Shall I proceed? If you have any doubts, you need any clarification regarding anything? Yes, that I will going to present the MATLAB model also at the end of the session. Okay. I will just to show the model at the end of the session after completing the controller design and all. Okay. Shall I proceed? Yes. Okay, this is a reason for harmonic generation. So you can see, okay. So coming to your need for PFC, so usually the setup will be like this. You have a AC voltage source. Here I have not shown the
Excuse me,
rectifier. Actually,
Umamaheswari
you
madam.
will have a
Kindly
rectifier.
go for full screen mode, pa.
Tell me.
Full screen.
Okay, 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 ma. Okay, so coming to need for PFC, so here just they have on the left side they have shown if you are not having any control source. What is that is what they have given it as a simple block diagram. You can see that without having any control, your harmonics will be injected into the AC voltage source. Why? Because your power converter, actually in the power converter here you're going to concentrate on SMPS setup only. In your SMPS you are going to have a diode rectifier followed by the DC to DC converter. So diode rectifier will make use of 4 diodes, which is going to be a non-linear device, as well as your DC to DC converter. Either it can use a single switch or two switches. So you are going to have a non-linearity in the DC to DC converter itself. So if you are not controlling the DC to DC converter, what happens? Harmonics will be injected in your AC voltage source. So your source voltage will get corrupted. But you need to comply with the IEEE standards. You know that your current harmonic should be your total harmonic distortion for the source current should be less than 5%. So you need to do some corrective action. So that is what is being represented as the right hand side block diagram. You can see you have a AC voltage source, then you are connecting a power converter with the cascade control strategy. Now cascade control strategy means it is going to implement two loops, outer voltage loop and inner current loop. Both the loops are interconnected. Okay, so when you incorporate a cascade control strategy, what happens? You will have harmonics, but whereas in your first diagram you can see that the amount of harmonics will be more. So the amount of harmonics will be less in the case of the power converter with the cascade control strategy. So what happens is whenever you are incorporating a cascade control strategy, what happens? The amount of harmonics gets reduced, so you can attain the unity power factor. That is going to be the first advantage, and the percentage THC will also be very low. Since you are suppressing the harmonic content, what happens? The efficiency will get improved, and you are providing a regulated output voltage under different operating condition also. So this is the need for PFC. So coming to PFC, you have actually two types. One is going to be passive PFC and another one is active PFC. In the case of passive PFC, you are going to use a passive components like inductor and capacitor for suppressing the harmonic. The problem with the passive PFC is when you incorporate passive PFC, what happens is your size becomes bulkier because you need to design one filter for each harmonic. Suppose if I want to design a filter for third harmonic, I need to choose a frequency as 150 hertz and I need to design my LNC. Similarly, if I want to suppress the fifth 250 hertz, what is the LNC required? Similarly, you need to design each for each becomes bulky, and it is also going to operate occupy very large space. Okay, that is one drawback. So in order to suppress that, you are going to use a active PFC. In your active PFC, we are just going to use a DC to DC converter available in the SMPS setup itself to correct the power factor. So when we do so, we have certain advantages. These advantages I have already mentioned. Just I will skip. So in your active PFC, when you want to incorporate, you should know you have two ways. Either you can go for double stage or you can go for single stage. In the case of double stage, what is it you are going to do is, my objective is to correct the current as well as to get the regulated output voltage. So in the case of double stage, you will be using two DC to DC converters connected in cascade. So one first converter, say it is going to be used for correcting the power factor, and the second converter is used for correcting the voltage, so that I am attaining a regulated output voltage. So in your double stage, you are going to incorporate two DC to DC converters. Two DC to DC converters are connected in cascade. The first DC to DC converter is meant for doing the power factor correction, and the second DC to DC converter is meant for doing the voltage regulation. So if you look at the size, the number of components required will be more, so the size will also increase. So you have to have more space for that, and the cost will also ultimately increase. Okay, so instead of going by double stage conversion, we'll go by a single stage conversion. So we'll be incorporating a cascade control strategy here, which will have outer voltage loop and inner current loop, such that you can attain a power factor correction as well as voltage regulation in a single loop itself by using a single controller itself. That is about your single stage. In my work, I have used only single stage converter because of the following advantages. It is going to have a reduced size and cost is very less, and the complexity of the circuit will also decrease if you make use of single stage. Okay. So coming to your single stage active PFC, actually you can either use voltage follower approach or multiplier approach. So in the case of voltage follower approach, what happens is you will be implementing an outer feedback loop. Okay, but what is the problem with the voltage follower loop is it is going to operate in discontinuous conduction mode. But if you make use of a multiplier approach, here you are going to use two controllers. One is meant for doing the voltage regulation, and another inner loop is going to implement source current shaping, thereby attaining power factor close to unity. Because of that, what happens is you can have the continuous conduction mode as well as discontinuous conduction mode operation. So because of that, what happens, the stress of the components will get reduced because of the reduced switching losses. What happens, we are going to have an increase in the efficiency. So we will be using multiplier approach in my simulation model, but I am going to operate only in continuous conduction mode. Okay, so coming to different control schemes, you have different control like average current control. So this is just to emphasize what are the inner current control strategy possible. Either you can use average current control, or you can go for hysteresis current control, or peak current control and nonlinear current control. So we will be using average current control mode only because of the following advantages. The first advantage is constant switching frequency, less sensitive to noise, and low switching losses and high power factor. As you already know, in the case of hysteresis current controller, you will be turning on the switch. You will be using a relay. You will be turning on the switch whenever the switch current falls. You will be turning off the switch whenever the switch current increases. Okay. So in the way you can turn on or turn off the switch in the case of hysteresis current controller, and similarly you can proceed with peak current control. So these are all some current control techniques. Since average current control technique will have advantages, we are just focusing on average current control technique. So coming to the DC to DC converter, though I have given a topic like DC to generally DC to DCT converter, but I have chosen SEPI converter here. I have because SEPI converter has some advantages over other converters. That is why SEPI converter is chosen here. So coming to switch to mode DC to DC converter, why it is called switch to mode DC to DC converter? Because you are going to operate the switch with a very high frequency. Okay, that is why it is called switch to mode DC to DC converter, and the turn on and turn off option of your switch will be very fast. Switch to mode converter basically it is classified into isolated converters and non-isolated converters. So we'll be focusing on non-isolated converter, and isolated converters we are not using it because we need to eliminate the transformer. Sometimes the transformer will create a saturation problem. So we want to have overcome the disadvantage. For that we have just used a SEPI converter in our work. Okay. Here, some advantages of non-isolated topologies over isolated being listed out. The first one is, as I said already, if you focus on your isolated topology, you can eliminate the transformer. Okay, and the cost will be very low, and the size will be small. Why? Because you are operating at a high switching frequency, weight will be very low, and you are going to suppress the harmonic, so you have low losses and efficiency will be more. So these are all some advantages of non-isolated converters available. As you already know, among the 4 types, whatever I have listed out, buck boost and buck boost converters are basic converters, and the derived converter is going to be Chuk converter and Sepi converter. We are not focusing on Chuk converter. Why? Because it is providing a inverting output voltage, and moreover, whatever switching stress for the your switches and MOSFET present in the system will be very high, okay, which is not advisable. So instead of Chuk converter, we'll be focusing on SEPI converter. I think it is well known, so I am not going to concentrate more over this. Okay, I will just go to my DC to DC SEPI converter. So I have used DC to DC SEPI converter because of the following advantages. Because I am going to get a continuous input current. Okay, input current is going to be continuous, and since if you use your Chuk converter, you are going to have the inverted output. But here it is not so. You are going to get a non-inverted output voltage, number 2. And the third important thing is you have low stress over your voltage and current stress over the semiconductor component. Preferably it is going to be diode and switches. That will be very less in the case of your DC to DC converter. And like your Chuk converter, this can be used for buck and boost operation. Either you can increase the voltage or decrease the voltage. You can set the desired duty ratio. Based on that, you can do the buck or boost operation. Okay, these are some certain advantages of your DC to DC SEPI converter. So here only my presentation starts. So first thing is, I'm going to model and design DC to DC SEPI converter. I'm going to use a reduced order model. So how to derive the reduced order model? For that, I have used a technique called moment matching method. Based on that, I have derived a reduced order model. Then the third step is to design a outer PI controller for voltage regulation. Fourth step is to design a inner current controller, which is going to be a LQR controller. Then finally, I'm going to just analyze the performance of the entire system by incorporating both inner loop and the outer loop. This is the methodology I have followed. This is about the design specification. I am operating at 50 kHz switching frequency and with a power rating of 100 watts. Okay. So this is about the converter parameter design. I think it is well known, it is available, but the output power I have designed for 200 watts here. Based on that, I have designed the output capacitance. An input inductor and output inductor is designed based on the ripple current you want. So you need to assume some ripple current percentage. Based on that, you need to design, and your capacitor you need to design based on the ripple voltage. Okay. So coming to the modeling. This is a circuit diagram which represents the DC to DC SEPI converter. So here we are going to focus on how it is operating during on stage of the switch and off stage of the switch. So whenever the switch gets turned on, what happens is the current through the inductors L1 and L2 increases. So what happens? Your diode, freewheeling diode, here you have a diode. That diode will get reverse biased. Why? Because you are going to have the energy stored by the inductor. So you have positive at the left extreme side and minus sign at the right side. Okay, right extreme side. So if it is so, what happens? You are going to have the reverse biasing condition of your diode. So your diode will get reverse biased. So your load current is being supplied just by your capacitor, output capacitor during on stage of the switch. Let me repeat, during on stage of the switch, the current through the input inductor and output inductor will increase. So your capacitor starts charging. But here, since your inductor will have the polarity like left side plus and minus sign at the right extreme side, what happens? Your free diode, which is present between your inductor, output inductor and capacitor, will get reverse biased. Because of that, it will be in off condition. So it is going to act as an open circuit. So the load current is being supplied by means of a output capacitor. Because as soon as you connect a supply, the output capacitor will get charged equivalent to your source voltage. So though your switch is conducting here, the charging action of your charged action of your capacitor, output capacitor is going to supply a current. Okay, because of that you are going to get a positive output voltage. So during during the turn off of your switch, what happens? Whenever the switch gets turned off, what happens? It is going to act as an open circuit. So when it is acting as an open circuit, what happens? Already when the switch is turned on, the inductor stores its energy. Whenever it is turned off, what happens? Your inductors L1 and L2 is going to discharge the energy. That because of the dissipation of energy by input inductors and output inductor, what happens? The diode gets forward biased here. So your current is freewheeling through the diode, and your output voltage will appear across your resistance R. Okay, this is about the operation. So coming to the modeling, you need to focus on mode 1 and mode 2. The point you need to remember while modeling is, you need to look into the number of energy storage elements in your DC to DC converter. Okay, whenever you want to choose a state variable, the state variable, number of state variable depends on the number of energy storage elements present in your converter. The number of energy storage elements present in your converter is 2 inductors and 2 capacitors. So totally you have 4 energy storage element. So when you have 4 energy storage element, it is going to be a 4th order system, and you are going to have 4 state variable for your DC to DC converter. So if you remember this point, you can model any converter. So the number of state variable is going to be based on the number of energy storage elements present in your system. Okay, so whenever you choose a state variable, you need to identify the number of energy storage element. For this given DC to DC SEPI converter, you can see that the number of energy storage element is going to be 4, 2 inductors and 2 capacitors. Okay, so totally 4 energy storage elements. So your state variables is going to be 4. So this is going to be a 4th order system. And one more thing is, while choosing a state variable, if you have inductor, you need to choose the current through the inductor as a state variable. And if you have a capacitor, you need to choose the voltage across the capacitor as a state variable. So this point you need to remember. So based on that, we will be deriving the state space equation. So state space equation is derived based on the switching on and off condition. So this is the equivalent circuit during mode 1. So when you have mode 1, you are going to have an equivalent circuit like this. As I said already, you are going to have 2 inductor currents, IL1, IL2, and 2 capacitors are present. So VC1 and VC2 are the 4 state variables. IL1, IL2, VC1, VC2 are the 4 state variables, and you are just going to apply a KVL and KCL for getting the state equation. That's it. Okay. So if you follow this procedure, you can obtain the state model of the any system. Okay. So now let us consider mode 1 circuit. So you can see that if you apply a KVL for the first image, you can write Vin is equal to L1 into dI1 by dt. So based on that, you can derive the value of dIL1 by dt. dIL1 by dt is Vin by L1. That is the first equation. Coming to the second equation, you can see that if you apply a KVL again to the second mesh, your voltage across a capacitance C1 will be equal to voltage across the inductance L2. That is L2 into dI, sum of the voltage across the capacitance C1 and the voltage across the inductance will be equal to 0. Because of that, you will be getting a second equation. So dIL2 by dt will be equal to minus VC1 by L2. So that is going to be the second expression. Next, we need to look into the current. Okay, you need to have a current. So here you can, in your second mesh, you can see that current through the capacitance C1 and current through the inductor L2 both are equal. So you can write like C1 into dVC1 by dt will be equal to IL2. So you can derive the expression for dVC1 by dt based on that. So dVC1 by dt will be equal to IL2 by C1. Based on that, we have derived the third equation. Coming to the fourth equation, you can see that in your mode 1, your diode D is reverse biased. Because of that, it is going to act as an open circuit. So if you look at the last mesh, that is a third mesh, which consists of the output capacitor and the resistor. You can apply Kirchhoff's current law here. You can see that the summation of current flowing through the capacitor C2 and current flowing through the load will be equal to 0. Why? Because it is in the, after that you have an open circuit. You can see that your diode is isolating your supply side and the load side here. So if you apply Kirchhoff's current law, you can write the fourth equation. Based on that, you can derive the expression for your dVC2 by dt. Why? Because current flowing through your C2 is going to be C2 into dVC2 by dt. So dVC2 by dt will be equal to minus Vc2 by Rc2. Since your load is connected in parallel with your capacitance, you can say that the voltage across your R will be C2 itself. That is why you are just taking it as Vc2 for the voltage across your R. So based on that, you can write the fourth equation. So you are just going to identify the state variable. After identifying the state variable, what you have to do is you need to just apply KVL and KCL to write the state equations for mode 1. Similarly, you can go for mode 2. In your mode 2, your switch will be in off condition, your diode will be in on condition. So you can see the circuit. This is the equivalent circuit for mode 2. Again, your inductor, current through the inductor IL1, current through the inductor IL2, and the voltage across the capacitors VC1 and VC2 are the state variable here. So if you apply the Kirchhoff's voltage law for the first mesh, you can write the expression for dIL1 by dt. Similarly, you can apply KVL for the second mesh. You can write the expression for dIL2 by dt. Then apply Kirchhoff's current law. So if you apply a Kirchhoff's current law, you can write the expression for dVC2 by dt, and the current which is flowing through your C1 and current flowing through the input inductor L1, both are equal. Because of that, you can write the expression, seventh expression, which is dVC1 by dt will be equal to IL1 by C1. Okay. So after getting a state equations during turn on and turn off conditions, you are just writing the equation in the matrix form here. So here, if for mode 1 they have written the matrix form, that is X dot is equal to A1X plus B1U. Okay, A1 is going to be the first matrix and B1 is going to be the second matrix. Okay, after that, what is it you need to do is, you need to write the similar equation for switch off condition. After writing the similar equation in the form of X dot is equal to A2X plus B2U, here you need to derive the value of the input matrix A and B. Okay, that is your objective. You know that in your mode 1, your duty cycle, let us assume like D. So during mode 2, your duty cycle is going to be 1 minus D. So you need to use D and 1 minus D for getting your equivalent matrix A and B. So we'll be calculating the value of, then again they have written one more equation which relates your output voltage. So if you look at the circuit, your output voltage is going to be V0 for both the modes, which is VC2. That is why your output equation will be like this, because Y is output equation. So Y is equal to just VC2 only for irrespective of mode 1 and mode 2. So you have one present at the right extreme side in your C matrix. Okay. So after getting A1 and A2 value, B1 and B2 value, you need to find out the equivalent matrix A. So for getting the equivalent matrix A, as I said already, let us consider D is the duty ratio during turn on condition. 1 minus D will be the duty ratio during turn off condition. So A1D plus A2 into 1 minus D, which is going to give the value of A. So you can get the expression for the matrix A here. Next, we need to get the value for B and C. So after getting ABC value, the feed forward matrix you need to calculate here. For this system, the feed forward matrix is 0. Why? Because you are getting the expression for Y as just Cx alone. X is nothing but a state variable, which is going to be IL1, IL2, VC1 and VC2. So D is 0 here. Hence feed forward matrix D is 0 here. So C matrix will be present. Next, you need to find out the transfer function. Why we are going by these steps is you want to design a controller based on your transfer function, because transfer function is actually defining the dynamics of the system. Dynamics of the system means during turn on, what happens to the current through the inductor, voltage across the capacitor. Similarly, during turn off condition, what happens to the dynamics of two inductors and two capacitors. That is being represented by means of a transfer function. So when you define a transfer function, it is actually defining the dynamics of the system. By using the transfer function, you can derive the controller. That's it. Okay. Now, the fourth order transfer function is obtained by using the formula C into Si minus A inverse into B plus D. So you can substitute the value of C, A, B and D. But here I have just given the value of A, B, C as a general value. But I already mentioned what is the C1 value I have defined. Okay, it is defined in your converter parameters. Okay, so those values you need to substitute for getting the A matrix and B matrix and C matrix. After getting A, B, C matrix, you need to use a formula like C into Si minus A inverse into B plus D for getting the fourth order transfer function. So this is the fourth order transfer function which shows the dynamics of the entire DC to DC SEPI converter. This DC to DC SEPI converter, I am going to use it as a power factor corrector. So what is the advantage of state space averaging technique is you have so many methods like circuit averaging, canonical modeling and all. But here it is just using the weighted average of the state space equation to derive the matrix for each mode. That is the first advantage. And here the dynamic behavior of the converter is greatly influenced by the nonlinear nature of the switching pulses, because you are going to derive the state equation in the form of a differential equation during turn on and turn off conditions. Why we are telling the switch as a nonlinear device? You know that you just take your diode. When you take your diode during turn on condition, its input impedance is going to be, input resistance is going to be 0. During turn off condition, its input resistance is going to be infinity. Since it is not obeying the Ohm's law, it is a nonlinear device. So in your dynamic model, what you are doing is you are just defining how about the state model during turn on and turn off condition of the switch. Based on that, you are going to derive the equation. So this will be very accurate method, and it eliminates the nonlinearity and simplifies the controller design. Okay, your switch and diode itself is a nonlinear device. So it is suppressing the nonlinearity, and it is going to provide a entire equation in S domain. Based on that, you are going to design a controller, and you are going to analyze the performance of the proposed DC to DC converter as a power factor corrector. That's it. And the fourth advantage is it makes the transient analysis simpler. And the fifth one is you can study the dynamic and steady state response. Okay, this is about your state space modeling approach. Then I will go to the next second objective. I need to derive the reduced order model. Why we are focusing on reduced order model? That is very important. Suppose if I want to incorporate the controller for a higher order system, I need to identify how many state variables present. So for my system, I have 4 state variables. So out of which I am going to concentrate on only 2 state variables, because just concentrating over 2 state variables itself is going to satisfy my requirement. So because of that, I am just going to focus on the output voltage and input current. Input current is nothing but current through the input inductor. Okay. So in the if you go for higher order model, you need to design a controller for 4 state variables, which is very complex, and whatever computation time needed for deriving the higher order model is also very tough. Okay, that computation time will be more. In order to reduce the computation time, and in order to reduce the complexity of the controller design, we are just going for the reduced order model, where we are going to focus on only the required state variable. In my case, the required state variable is going to be output capacitor and input inductor. Why? Because That output capacitor is meant for removing the ripples present in the output voltage so that I can get the regulated output voltage, and input inductor, that is L1, which is present in your DC to DC converter. I'm going to focus on. Why? Because if I suppress the current harmonics in my input inductor, I can indirectly suppress the harmonics present in the source side, because prior to that you have a AC to DC converter. So when I do corrective action for my input inductor current, it will have impact over my source current. So that is why I'm going to focus only on 2 state variable instead of focusing on 4 state variable. That is why I'm going to use this reduced order model. Okay, coming to the derivation of the reduced order model, my system is going to be a 4th order model. So I told how to derive the transfer function. Next, what I'm going to do is I'm just going to use a long division method. By using the long division method, I'm going to just find out the expression for my power series. So the power series expansion of G4Fs is given in equation 19. Then I'm just going to compare this G4Fs with G of S. G of S is the general equation. After comparing that, I can identify what is the value of my constants C0, C1, C2 up to Cn. Okay. So after getting the value of my C0, C1, C2 and Cn, okay, so I am going to get the value for C0, C1, C2, C3 and C4 and C5. So after getting these values, by using my moment matching method, I am going to derive by using moment matching method only. You have so many model order reduction method, but I am just using a preliminary method for deriving the reduced order. So as per the moment matching formula, the value of coefficients are found to be A31, A32, A33 you need to find out. Similarly, you need to find out from A21 to A23. They have already defined the formulas. By using the formulas, you can just substitute the value of your C0, C1, C2, C3 and you can get the value of your A21, A22, A23. Similarly, A31 to A33. After getting these values, I need to substitute the values for this is the formula actually they have given, that is the formula 22 and 23 equations. It is just describing the formula, and equation 24 and 25 is describing what about the value of A21 to A23 and A31 to A33 when you substitute the value C0 to C5. Okay, so after that, by just using the formula, this formula is already given in your moment matching method. You need to just substitute the coefficient value A31 to A33. Similarly, A21 to A23. So you will get the reduced 3rd order model. Okay, you can see the power of S in your denominator. It is 3. So it is the 3rd order model. But I want to suppress only what? I want to focus on only 2 state variables. So because of that, I need to derive the 2nd order reduced order model. Again, I need to go by the procedure. So I know what is the 3rd order model. After substituting A21 to A23 and A31 to A33. So I will get G3 of S. Again, I need to do the power series expansion by just applying long division method. So if I apply long division method, I will get one series. That series I need to compare with the general coefficient series, whatever I have mentioned already. Then I need to again find out the value from C0 to C5. Again, you just look into the parameter calculation. That is, we need to calculate A11, A12 and A21 and A22. So after substituting C0 to C5 in your A11, A12, A21, A22 equation, you will get the values. So that which is represented as equation number 33 to get a reduced order model, which is going to be G2 of S. Okay, so this is G2 of S, which is just representing the 2nd order reduced order transfer function, 2nd order transfer function of my DC to DC septic converter. Okay, this is the procedure you need to follow. Let me repeat. Just to go to your 4th order model, using long division method, get the power series expansion, which is represented as equation 19. Then you need to compare the equation 19 with the general expression in order to get the coefficient C0 to C5. After getting C0 to C5, you know the formula for A21 to A23, A31 to A33. It is already given in moment matching method. Just to substitute, get the coefficient value. After getting the coefficient values, just to substitute in the general equation, which is represented in equation number 26, get the value of your G3 of S. After getting G3 of S, it is just to represent in the third order model. You need to focus on the second order model. Again, you need to apply a long division method. Then just to apply the power series expansion, compare it with the general power series, get the value of C0 to C5 again, substitute in the formula for A11, A12, A21 and A22. Then substitute those values in the general equation expressed in equation number 33 and get the value of your G2 of S. So this is the procedure you need to follow. After getting the second order and the fourth order, you need to compare the step response of your fourth order model and the second order model. Here you can see the comparison. Both are going to provide the same transient response. You can see the peak overshoot values and settling time value, rise time value, steady state value and both are matching. So we can just proceed with your reduced order model so that you can reduce the computational time and you can easily design the controller. Because designing a controller for the higher order model is going to be little bit difficult. So we are just reducing the model to second order model so that your computation time will get reduced as well as you can easily design the controller. That is my objective. Okay. You need any clarification regarding this? You need any clarification regarding the presentation, whatever I have done so far? Shall I proceed? Okay. Okay. Now comes the controller design. Coming to the controller, I said we are going to use a outer PI controller and inner LQR controller. For designing the outer PI controller, I have incorporated the conventional tuning method called Ziegler-Nicholas tuning method. So I need to have I need to construct a block diagram like this. So I have a transfer function here. Along with that, I have connected a PID controller. So after connecting a PID controller, I need to operate in closed loop. My reference is going to be a step input. I'm going to feed a measured output through the feedback gain, which is taken as 1 year. Now what I have to do is, for tuning by using ZN method, I just have to incorporate P controller alone. I need to keep the value of my KD and KI as 0. So introduce only proportional controller gain by setting minimum values of integral gain and derivative gain. So what you have to do is, the next step is, after giving KP value and K and KD are made as very small or it is made as 0. Okay. After that, you need to keep on increase your controller gain KP such that I am getting a sustained oscillation. After getting a sustained oscillation, I need to measure ultimate period PU and ultimate gain KU. You know, representing the KU value, and PU is nothing but period over a cycle. So you just measure the value of period and measure the value of ultimate gain. After getting the ultimate gain and period, you can get the value of KP and KI by using the Ziegler-Nicholas tuning formula. This formula is fixed. The formula says KP can be. So if you divide the ultimate gain by 2.2, you will get the value of KP. KI can be got by dividing the period by 2. So you will get the value of KI. So the KP and KI value for my system is found to be 0.3 and 1.5. This is about the outer voltage controller design. Let me repeat. So for designing the output controller, what you have to do is, you need to adopt ZN method. For adopting the ZN method, you need to construct a closed loop like this. So if you construct a closed loop, you can see that you are going to connect a transfer function block with a PID controller block. Then you are going to have a step input as a reference, and you are going to measure a feedback gain like that. Okay. Then you keep the minimum value for your PI, KP, and you just start with the minimum value for KP, and you keep your KI and KD as a constant one, which is going to be negligible, or we can take it as 0. Just increase your KP from the small value. For one particular value of KP, you will get a sustained oscillation. This is what a curve I got from the sustained oscillation. Sustained oscillation means what? You will have a constant amplitude and frequency for the output waveform. So you need to measure the value of M, measure the value of period. After getting the value of peak and the ultimate period, just to substitute in your KP formula and KA formula, get the value of your PI controller. Next comes the design of inner LQR controller. For designing the inner LQR controller, I'm just going to concentrate on optimization control. The theory says that we need to we need to concentrate on optimal control with the dynamic system which is operating at a minimum cost. Okay, we will be using a time invariant linear quadratic regulator as a current regulator here, current controller here. The thing is, I have to construct a controller U is equal to minus kx such that I can minimize the cost function. Okay, that minimization of the cost function is called linear quadratic regulator problem. So linear quadratic regulator controller is based on the optimization problem only. Like your power system, here also our objective is to minimize some cost function which is called performance index. Okay, we need to minimize the cost function, and we need to derive the control law for minimizing the cost function. That's it. So here you can see the cost function which is represented as J, which is given as off into x transpose qx plus off into u transpose into ru into dt. You need to integrate between t1 to tf. Okay, so this is what the cost function. I want to construct a controller. I want to design a state feedback controller U is equal to minus kfx to minimize the quadratic cost function J. Okay, subject to the system dynamics, x dot is equal to ax plus bu. Now I know what is the value of A from my state model. B value I know, but I need to choose two matrices. The two matrices are called weighing matrices. Q and R are called weighing matrices. The condition for choosing Q and R is Q should be positive semi-definite and R should be positive definite. Okay, that is the condition. Based on that, I am going to choose my Q and R value. While choosing R, you will be definitely choosing like just one. Okay, 1 by 1 matrix will be chosen as R for designing a LQR controller. But while choosing Q, you will be careful. You should be careful. Why? Because you need to give a maximum weightage for the parameter whatever you are going to control. I know that I have an outer voltage controller for doing the voltage regulation. My objective is to do the corrective action for inner current. For that, I am going to give more weightage. Okay, based on that, I am going to choose my Q value. So the value for choosing your Q should be correct. Then only your controller will operate effectively. So in the case of LQR controller, my objective is to minimize the cost function J. I have given the cost function J by means of some controller U is equal to minus KF into X. KF is nothing but a gain matrix. Okay, gain matrix that negative represents, we will always apply a negative feedback in order to maintain the stability. As I said already, Q and R should be selected in such a way that Q should be positive semi-definite and R should be positive definite. So here I have chosen Q and R value. You can see R value is chosen as 1 by 1 matrix. Q value I am going to choose it as 2 by 2 matrix. In that, preferably I am going to give the value of Q11 as a maximum value, because that is only going to define how much corrective action I am going to provide for my inner current controller. the next diagonal element, you can see you're just giving 1, even you can give 0 there, because it is just defining the corrective action for your output voltage. Already you have PID controller for taking the corrective action, so I am not going to concentrate more on Q22. I just concentrate on Q11 value. While I concentrate on Q11 value, if I choose the appropriate value for Q11, what happens? I can do more corrective action and I can shape the current so that I can attain the power factor, which is unity. Okay. Now you will be just for substituting the value of Q and R in your first equation, that is 35, equation number 35. You are substituting. After that, you should know what is control law. Control law, as I said already, which is nothing but what? Minus KFX. Usually the control law is U is equal to minus KX. But here, since we are applying feedback control, we have just taken a suffix as F here. So minus KFX is going to be the control law, which is equal to minus R inverse into B transpose into QX. Now my objective is to solve for the value of KF. Okay, this KF is called gain matrix, whereas here you have K, that is representing the return function matrix. So that return function matrix K can be solved by solving the Riccati equation. So I have a Riccati equation. It is already available in your optimization principle. So just to go through that, you need to substitute the value of Q, substitute the value of A, and substitute the value of K. K value is not known. Your objective is to find out the value of K. Just K value is taken as 2 by 2 matrix with unknown parameters, and A, B matrix and all you know from the state model. Just to substitute and get the answer for your return function matrix K. So after getting the return function matrix K, you need to substitute the return function matrix K in your equation 37. You can see that K, you want to get the gain matrix KF. So KF is nothing but what? Minus R inverse B transpose K. So R inverse B transpose K is nothing but your KF. So you know the value of the return function matrix K, that you substitute, get the answer for your KF. So after getting KF, you can construct your LQR control law. So LQR control law is nothing but U is equal to minus K1 into error. Error is nothing but what? Reference current minus the inductor current. Similarly, K2 is nothing but reference voltage minus output voltage. So error 1 and error 2 you need for implementing your LQR controller. So when you incorporate LQR controller, you can see that whichever parameter you want to control, that should have more gain value. So for that gain value only, we have chosen the value of Q1 as very high in the case of LQR controller. So you have got the value of U. Based on that, you are going to construct your LQR controller in order to implement the closed loop. That's it. So let me repeat. So in the case of LQR controller, you need to construct a control law. U is equal to minus KF X to minimize the cost function, this one. So when you want to minimize the cost function, what you have to do is you need to design a controller U is equal to minus KFX. Okay. So that KF is defining a feedback gain matrix. Okay. Now what you are doing is you are just substituting the value of your Q and R in the cost function. This is the final cost function you want to minimize. For this, you have to construct a control law. The control law is nothing but U is equal to minus KFX, where KF is equal to R inverse B transpose K. That K is representing the return function matrix. So that return function matrix you need to solve by using Riccati equation. You need to use a Riccati equation. It is available. Okay, you just substitute the value of Q, substitute the value of BA. K is unknown, then get the value of your K. So after getting the return function matrix, you know what is KF. KF is nothing but what? R inverse into B transpose into K. By using that formula, you can get the value of your K. Okay, that is nothing but your gain matrix, feedback gain matrix. Here you got the gain matrix as 85.238, 0.045. So you can see that the gain for the inner current loop will be very high, whereas the gain for the voltage loop is very less. Why? Because the voltage loop will be taken care of by your outer voltage controller itself, and your control law is going to be U is equal to minus K1 E1 plus minus K2 E2. So K1 is nothing but 85.238 and K2 is nothing but 0.045. That E1 represents the current error and E2 represents the voltage error. So equation 41 is representing the final control law, which is going to minimize the cost function, whichever is mentioned already. Okay. So this is about the LQR design. So after implementing the design, after calculating the gain value, you need to go for the closed loop control using LQR. You can see the block diagram here. You have a SMPS setup. SMPS setup is single phase supply with a diode bridge rectifier connected with a DC to DC SEPI converter. So I am going to operate the DC to DC converter MOSFET with a high switching frequency in such a way that I am obtaining a resonant condition so that the circuit is equivalent to diode rectifier connected with the R load. My DC to DC SEPI converter is going to act as an emulator here, resistor emulator here, so that I have a circuit which contains diode rectifier with the R load. So my source current and source voltage will be in phase so that I can attain the power factor close to unity. That is my objective. So for that I am implementing the closed loop. I am just sensing my output voltage, compare it with the reference. The error is given to the outer voltage controller. The outer voltage controller parameters are tuned by using ZN tuning here. Again, I need to generate the reference current for my inner loop. For that, what I am doing is I am just sensing a source voltage here. Source voltage is sensed and it has been divided by the value of K in order to get the unit template. That unit template is multiplied with the outer voltage PI controller gain, so that I am getting a reference current. That reference current is compared with the inner current controller. Okay, so you will get a error. So by making use of the error E1 and E2, I am going to construct LQR controller so that I can generate a gate pulse for my switch. So when I generate a gate pulse for my switch, I can get the output to regulated voltage, as well as I can shape the source current so that it is in phase with the source voltage. So I can attain the power factor which is close to unity. So this is what the diagram Simulink model is represented here. You can see that you are sensing the output voltage. Similarly, you are sensing the inductor current from your DC to DC SEPI converter. So output voltage is compared with the reference voltage. You are getting a error. Error is being given as an input to your PI controller. Again, the PI controller and V rectified voltage is multiplied to get a I reference. I reference is compared with the ILI to get a current error. After getting a current error, you can see that E1 error is being multiplied with your K1, E2 error is multiplied with your K2, both get summed up, which is going to form a control law U is equal to minus Kx. Then it is compared with the carrier to get a PWM pulses. This is what is happening in the case of my LQR control. Shall I go for Simulink model? Shall I go for Simulink model? Is it clear? You have any doubt? Yes. Okay. Yes. Okay. You can see the single phase diagram here. Okay. Single phase which incorporates the LQR controller. So you have a supply here. Supply single phase voltage is rectified by means of a diode rectifier. Then you have a DC to DC SEPI converter. Then, as I said already, you are going to sense the output voltage, and that voltage is compared with the reference voltage. 100 is reference voltage. Then the error is given to the PI controller here. You can see the PI controller model. The PI controller output is multiplied with the rectified voltage to get a reference current. Here you can see you are getting a reference current. That reference current is compared with the inductor current. So you have two errors. One is going to be the outer voltage error, and the another one is going to be inner current error. Both the voltage error and current error. You can see here I have used a multiplication block. So I have multiplied that error 1 by means of error 1 is nothing but outer voltage error. That needs to be multiplied with the gain K1, which is 0.04. Similarly, the inner current error is multiplied with the gain 85. That is what I got the gain by using LQR controller. Both get summed up by using a summer. Then finally, that summed up voltage, equation. I mean, it is nothing but a control law that is compared with the carrier of Ricketts switching frequency, so that whatever pulses I am getting, that is being given to, you can see the pulses are given to MOSFET switches. That's it. Okay, you can see your pulses are given to MOSFET switch. This is the Simulink model of single phase system, and just simulating this, you can see what is the output I am getting. I think it's running now. So my objective is to get the output voltage 100, and I need to regulate, I need to shape the source current. You can see the total harmonic distortion block here. This is connected to the display. As per IEEE standard regulation, you need to get a current PhD percentage of less than 5%. It is preferable. So you need to multiply by 100. Okay, you need to multiply by 100 in order to get the THD percentage. Already it is 0.016. If you multiply by 100, you will get 1.6% as a THD percentage for the source current. I think it is settling down at 100. So I have two objectives. I cannot use only this, I cannot use a single controller for single objective. So because I am implementing cascade control strategy here, I need to have two objectives. One objective is to regulate the output voltage, and another objective is to shape the input current with a low percentage THD, so as to have a power factor close to unity. I think I can stop here. I'll just to show the output voltage waveform. It is responding slowly. 1 second. I think I need to change the this parameter. Or I will use command window. I will just use command window for getting the for showing the output voltage. One second. I think I have used different variable for my clock T. Clock T, comma. 1 second. V naught. And see. Okay, I have stopped the simulation. So my voltage is regulated. You can even see the source current. Source current. You can see the source current. Source current, you can see it is shaped. It is in phase with the source voltage. In phase with the source voltage. That is why I am getting a THD percentage of 1.6. Okay, you can see the THD percentage, and my output voltage is settled at 99.38. I need to increase the filter value so that I can get almost 100. Okay, so this is about the implementation of LQR control for single phase system. But I need to focus on how to calculate the power factor value. So I have just given the power factor calculation is you need to get the instantaneous value of RMS. Instantaneous value you need to multiply. So instantaneous value of voltage and current is multiplied, and it's been given to your low pass filter with the pass band frequency of 300 hertz. And again, you need to calculate the RMS value. Okay, RMS value for your voltage and current. Product value you need to find out. After that, if you divide the real power by apparent power, you will get the power factor. Since we are using an ideal component, it is showing 1.002. Actually, it is 1.1. Okay, the power factor is 1. You can see the efficiency is also 92.38%. You need to multiply by 100. Here they have just given output voltage by input voltage. That's it. So if you multiply by 100, you will get the efficiency value as 92.38. So this is about the implementation of LQR controller for single phase system. You can study for different variations. You can vary the load, and you can see whether you are attaining the required voltage and the required current. Similarly, you can vary the set point, or you can vary the line voltage in order to see whether the controller is effective enough. That's it. Okay, this is for single phase system. Similarly, you can execute for three phase system. You can see the three phase system. In your three phase system, what we have done is, 1 second, I'll just go to the slide. In your three-phase system, for implementing the closed loop, we have used 3 diode bridge rectifier individually being given to a three-phase supply. Then each diode bridge rectifier is connected to DC to DC SEPI converter. So you have DC to DC SEPI converter modules. For implementing the closed loop, what we have done is we have just measured the output voltage. Here you can see that DC to DC SEPI converter are connected by commonly connected by a single filter capacitance and single load. Okay, other structure of converter remains the same. Okay, so you are sensing the output voltage, comparing it with the reference voltage, and the error is fed to the PI controller, which is taken as E1. Okay, for generating a reference current, you need to again get the template from the three-phase supply, multiply. You are supposed to get only unit template, then get the reference current for 3 phases, then 3 supply current you are measuring, comparing it, and you will be getting a error. So you need to incorporate 3 RO LQR controllers for do the corrective action. So you will get 3 PWM pulses from 3 RO LQR, and that pulses are used for exciting your MOSFET switch present in your DC to DC SEPI converter, so that you can attain the regulated output voltage as well as you are shaping all the 3-phase current. This is what is happening in the case of your 3-phase. You can see the 3-phase system here. So you have 3-phase supply. We have used an isolation transformer with the ratio of 1:1. So you can see this is going to be the first supply fed with the first rectifier, then first SEPI converter. Next, second Y phase is being connected to again one more bridge rectifier, then again one more SEPI converter you have connected, and third phase B phase is connected to diode rectifier followed by a DC to DC SEPI converter. Okay. Now, as I said already, all the 3 will have output inductor and diodes, isn't it? The diode is being connected to common filter capacitor here. You can see diode is connected to common filter capacitor and common load. So the load remains a single load here. So you are going to apply only single outer voltage loop here. So just to sense the output voltage is sensed, compare it with the desired voltage 100, then get the error. That error is given to outer PI controller. PI controller output is common for all the 3 phases for generating a reference current. So you need to get a template from the unit template from the source voltage. So get the source voltage A and source voltage B, source voltage C, and get the corresponding unit template, multiply with the outer PI controller to get the reference. Okay, reference current for 3 phases. After getting the reference current for the 3 phases, measure the current, inductor current from 3 phases. So you have 3 DC to DC SEPI converter, measure the current. Okay, when you measure the current, you have a calculation of error. That error is being given to LQR1. You can see that we have incorporated again K1E1 plus K2E2 concept only. So you can see that K2 is going to be 85.238 and K1 is going to be 0.045. This is what you have obtained in the case of your LQR controller. So separately, you are going to have 3 LQR controllers for doing corrective action for 3 switches present in 3 SEPI converter modules here. Okay. So after incorporating LQR controller, you will be comparing it with the carrier to generate a PWM pulses for the corresponding switch. So you have 3 PWM pulses. 3 PWM pulses are given to 3 MOSFET switches. Okay. So for again calculating power factor, you will be calculating the real power by just multiplying by your instantaneous value of, that is RMS value of the voltage and current. Then you are calculating the apparent power. What you have to do is, after getting the power, you need to use a filter. So real power by apparent power will give the power factor value. The same formula is applied here. Here in each phase you can connect a THT in order to measure the THT percentage. Okay. So let me run. Running now. So here you have a output voltage block. You can see the output voltage block here. I will just zoom it. You can see the outer voltage loop and the corresponding outer voltage measurement. So it has reached 98.79, I think so. Okay, it has got the, I think it will reach 100. You can see the source current. Source current THD is not 34. If you multiply by 100, 3.4%, which is, the information provided by the IEEE is we need to maintain the percentage THD below 5%. Okay, it is possible for all the phases. You can see for R phase, Y phase, and B phase. You can see. Let me show the current waveform. Current waveform, I think. You can see the current waveform. You can see the current waveforms. 1 second, I have problem with my mouse. You can see the current waveform. So it is also sinusoidal. Each phase also you can see. So for the R phase, it is like this. Okay. R phase, then Y phase. It is inductor current. 1 second. For Y phase, we have here. So you can see it is sinusoidal only. Source voltage and source current are sinusoidal. Or Y phase. Then for the third phase, you can see it is sinusoidal. So all the three phases are sinusoidal. All the three phases are maintaining a power factor close to unity, and you can see the voltage obtained is 99.99 volts, and you can even look at the power factor also, which is 1.00. So we can attain the power factor close to unity now. Okay, for by using a cascade control strategy, which is employing the outer PI loop and inner LQR controller. That is a conclusion. Here I have just shown the waveforms related to. These are all some simulation results which is obtained for single phase system. You can see the source voltage and source current is in phase. This is for rated load condition, and the THD percentage is 2.446 for your rated load. Again, you can see the output voltage which is well regulated, and the settling time is found to be 0.06 seconds. Okay, and the second waveform which is showing what happens when you apply a load variation at different timings. So here they have introduced a load for 20% decrease in load. What happens to the voltage, load voltage? You can see the load voltage is settled after some time, which is 0.6 seconds. Similarly, you can apply a voltage 20% increase in load. It's been applied at 3.5 seconds, and it is settled after 0.6 seconds. So the second curve is
Excuse me, Uma
representing the
madam.
variation.
Full screen mode, ma. Kindly
Ah.
keep it in full screen.
Okay. Fine. Just I think you can see the waveform now. Okay. Prior to this, I have shown the waveform for rated load. You can see source voltage and source current are in phase. This is for single phase, and corresponding THD spectrum I have shown here. The THD percentage is 2.446, and it is less than 5% as per IEEE 519 standard. Next, you can see the output voltage is well regulated, and it is settled at a settling time of 0.6 seconds. The next waveform, it is just showing what happens when you have a load variation. If you apply a load variation, 20% decrease in load, what happens, and 20% increase in load, what happens. I think the output got settled after 0.6 seconds for both the cases. The second waveform is showing the variation of source voltage with respect to source current. Here also, if you expand, you can see that source current is sinusoidal irrespective of the load variation applied at 2 instance. Okay. Next shows the reference voltage variation. Here I have actually kept the reference voltage as 100 volt. Instead of 100 volt, they are varying 100 volt to 120 volt at 1 second. Similarly, they have given a variation at different point. You can see at 4 instance they have varied the set point, which is nothing but a reference voltage. So though they are varying the reference voltage, it gets settled. You can see if I give 120 also, my controller is effective enough to track that 120 volt. Okay, va? So my reference voltage is actually 100 volt, but I am keeping it at 120 volt at an instant one, but my controller is effective enough to track the reference voltage too. Okay, this one again you can see the second waveform, which shows the variation of load with respect to your source current. Source current waveform is maintained. It is purely sinusoidal irrespective of the change in the reference voltage variation also. But you can see there is a magnitude change, but the current remains, shape remains same. Okay. The final one is just representing what about the variation of source current with respect to load current. Okay, you can see. Next is going to be a line variation. Line variation means source voltage actually I have kept at 50 volt RMS. Now I am varying 50 volt to 60 volt at 1 second. What happens? Similarly, I can give line voltage variation at 4 instance, and I am just noting down what happens to my output voltage. You can see the voltage is regulated for low supply voltage variations also. Similarly, the source current is maintained constant. My objective is to regulate the output voltage and make the source current sinusoidal so that I can keep the power factor close to unity. That's it. So that is what I am obtaining for all the 3 variations here. Okay. So here just they have given the comparison between the conventional PI controller and LQR controller in terms of settling time, power factor, and percentage THT. Okay, so and I told the 3 parameters whatever we are varying is load variation, reference voltage variation, line variation. For 20% increase and 20% decrease, what happens to the settling time, what happens to the power factor and THT, we have just analyzed, and you can see that in the case of LQR controller, settling time is not, you are not having much variation in the settling time. For line voltage variation only, we are getting a less settling time. But if you compare the power factor is almost maintained unity, and you can see that the percentage THT is also well below 5% as per IEEE 519 standard. Okay, so this is regarding the comparison. This is what the waveform I am obtaining for the 3-phase. So I have just explained how to incorporate your LQR controller for 3-phase system also. And this is just a output, parameter values. You can see the waveform. First one is going to be a source current. So this you can obtain by using a plot command. So you can see all the 3-phase source currents are sinusoidal. In order to differentiate 3 phases, I have given RYB color, and you can see that your output voltage is also well regulated. My reference voltage is 100 volts. My controller is effective enough to track the reference voltage also. And last 3 waveforms, it is just representing how the source current is with the source voltage. You can see that for all the 3 cases, source current is in phase with the source voltage, and I can maintain the THT below 5% as per IEEE standard. Okay. In order to differentiate the current and voltage, I have given current color as green. That's it. But the voltage and voltage is maintained as just RYB. That's it. Okay. This is about the implementation of LQR for shaping the source current in order to attain the unity power factor. And one more objective is to get a regulated output voltage. That is also we are getting. And these are all some advantages of LQR over other controllers. The response is going to be fast compared to other controllers. And it provides better performance for all operating conditions. Here I have analyzed for line load and set point variations. So we can see that we can achieve the percentage THT well below 5%, and we can get the regulated output voltage for all the 3 conditions. Okay. But if you compare the other controller, here we need to weigh which states are more important. As I said already, we need to focus on inner current controller. So we need to have we need to give more weightage for the Q11 value while choosing your weighing matrix Q. Okay, that is very important. And one more important advantage over state feedback controller is, as you already know, state feedback controller is designed by using the desired closed loop poles. Sometimes if we by the mistake we might have chosen the closed loop poles which are nearer to right of plane, means the system may become unstable. So that problem will not arise in the case of your LQR controller. Okay, that problem will be present in the case of state feedback controller, and here no steady state error. You will get almost zero steady state error only. That's it. Okay. Thank you. In case if you want to ask any question, you can ask.
Thank you, Uma madam, for your valuable presentation, and you have shown the live simulation of single phase as well as three phase circuit with the results. Thank you very much.
Okay, thank you, madam.
Questionnaire sections.
Thanks.
Sai Kumar sir.
Okay. Thank you, Pa. Ashwini Kumar. Thank you. Thank you. If you need any clarification regarding this, you can ask. You can ask questions, man. Even if you're hesitating to ask in person, you can use the chat box and you can message me if you need any clarification regarding this. Okay, you can go for one person. Anand Nagarajan, he has asked, can you suggest some other controller than LQR? You can use sliding mode controller. Okay, I have also implemented sliding mode controller. Since sliding mode controller is a variable structure controller, you can use that in order to get more accurate result than LQR controller.
Participants, any other questions from your side regarding the topic? Please do ask.
In case if you need any clarification regarding this, you can ask.